All right, we're going to wrap up this chapter by looking at just a couple more ways on how matter is organized, how it's classified, and then talk a little bit about the types of changes that matter undergoes and some of the properties associated with these types of matter. So I want to take a look at the very smallest part of matter that you can get to, and this is called an atom. Now, in further chapters, we're going to break down like what an atom is made up of, but right now, the definition of an atom is it's the smallest particle of an element that still has the properties of that element and can enter into a chemical combination. And that just means it can still react to make compounds. So, for example, here is you can see on the left there's a chunk of gold. And if you were to take that gold nugget and cut it in half, you get a small, two smaller halves. And then you cut it in half again and again and again. Eventually, if we had, the tools to do this, we would cut it down until we reach exactly 1 atom of gold. And at that point, you could not divide that anymore. In fact, that's what the name atom is based off of. Atom comes from the Greek word, atomos, which means indivisible. And on the right there, this is a picture from what's called a scanning tunneling microscope. And that, even then, doesn't give us a complete picture of an atom because all of these little spheres, I'll try to maybe zoom in a little bit, but like this little sphere, like right there, that's an atom. And that's kind of like how we have to observe atoms is like in a very, very large group. We can't really get any more magnified than that. And so, yeah, like here's another atom of gold, and there's an atom, and so on and so forth. And to give you an idea of just how small an atom is, I want you to envision this. Pretty much like one of the smallest things that we can see with our eye is a single strand of a spider's web. Now, the one of the atoms that makes up a spider's web is carbon. Carbon is very prevalent in that. And the relationship or the relationship in size between one single carbon atom and the whole strand, just well, again, one single strand, think of how thin that is like if we were to take a dime and put it in a football field. That's the comparison of the size of one carbon atom to that very, very, very thin strand of a spider's web. So atoms are very, very, very small particles of matter. Now, when atoms combine together and form bonds, they make molecules. So molecules are two or more atoms joined by strong forces called bonds. Now we're going to dive deeper into chemical bonds a little bit later in further chapters. So you don't need to worry like, well, what is that? Like, how are they joining? They're joined right now. Just know that they're joined by forces called bonds, and there's very few actual elements that exist as like free atoms. Even some that you're familiar with, like for example, hydrogen and oxygen. When you breathe, you're not breathing in individual atoms of oxygen. Oxygen exists as what we call a diatomic molecule. It's two atoms of oxygen bonded together. And as I said, there are very few atoms that exist as free atoms. Some that I can think of are like helium and neon and argon. Those atoms kind of float around and do not associate with each other in either way, in any sort of way. But most other atoms on the periodic table or other elements, their atoms associate with each other and are bonded to each other in some way. So you can kind of see some examples of that, like I pointed out hydrogen and oxygen. Phosphorus. Phosphorus is an element on the periodic table, but exists as this molecule of four phosphorus atoms bonded together. Sulfur as well. One of the forms of sulfur, there's a few of them, has 8 sulfur atoms bonded together. We can apply this to things that have different elements in them. I've used water a whole lot in our examples, but water is composed of hydrogen atoms and oxygen atoms. Carbon dioxide. Carbon dioxide is made up of carbon and oxygen, two different atoms joined together by bonds. The compound glucose, that's something we've heard about. Well, glucose is a lot of carbons, a lot of hydrogens, and a lot of oxygens bonded together in a certain way. And so, again, just to review, a molecule is two or more atoms. They don't have to be the same, but can be, but two or more atoms that are joined by strong forces. Now, let's talk a little bit about the properties that define these molecules and these atoms. There's two types of properties we're going to look at. The first of these um, are physical properties. These are properties of matter, not associated with a change in its chemical composition. That means as long as you don't physically change the identity of the compound, you don't break it down or separate its atoms out or the molecule, those properties are always going to be the same. These are things, for example, and this is a small list, it's not exhaustive, but things like density, color, hardness, melting point, boiling point, electrical conductivity, and so on. So those are always constant for every single sample of that molecule. So you have one sample of water, it's going to have the same boiling point as another sample of water. Now, if you were to do some sort of chemical change to that water so that it wasn't water anymore, then the physical properties are not going to be the same. Now, associated with that are changes that deal with physical properties. So a physical change is a change in state of matter without a change in the chemical identity. For example, if you melt an ice cube, okay, well, ice is solid water. If you melt it, is it still water? Yeah, absolutely. It's just in a different state. If you take that water and then you put it in a pot and you boil it, is it still water? Yeah, it's just changing to gaseous water, it's changing into water vapor. Um, let's take sugar, for example. When you dissolve sugar in coffee, is it still sugar? Yeah, it's just in very, very smaller particles floating around in coffee. If you were to boil all the coffee away and get rid of all the other compounds that are in there, you would get that sugar back. Or like for example, steam condensing, so liquid water. Steam is gaseous water. When it hits a cold surface, it will condense and just go to liquid water. It still has the exact same properties. Steam has the same properties as liquid water does. It hasn't changed its identity. Now, on the flip side of that, let's talk a little bit about chemical properties. Chemical properties can be defined as the ability or inability to change from one type of matter to another. The simplest way to describe a chemical property is it involves the chemical reactivity of a particular substance. So like, for example, let's compare iron to chromium. And you look at that and say, well, that looks like rusted iron. Exactly. That's what iron looks like after it's sat in contact with water for a long time. Iron has a very high susceptibility to be oxidized, or when you add oxygen to it, it reacts a lot with oxygen. And it makes a substance known as iron oxide, which is just rust. Chromium, on the other hand, is very resistant to oxidation. And so iron's um, propensity to react with oxygen and chromium's resistance to react with oxygen is a type of chemical property. Some other examples are like flammability. Certain substances burn very well, and others are very resistant to being ignited. Or toxicity. Toxicity, a measure of how you can kind of look at how dangerous it is to the human system. How does it react? Sorry, I can't spell right now. Toxicity. Um, how does it react to the human body? What kind of chemical reaction does it cause in the human system? Or something like acidity. We'll talk a lot about acids and bases, but a compound to act like that or not act like that is an example of a chemical property. Now, associated with those are chemical changes. You can kind of, if physical changes deal with states, changing of states of matter, but the compound's still the same, a chemical change, you can kind of start thinking, well, it deals with, changing a substance from one thing and completely changing its identity. So a chemical change produces one or more types of matter that differ from the matter before the change. A simpler way to kind of put that is if you take a substance and you do a chemical reaction and it's not that substance anymore, it's something else, that's a chemical change. And, again, I'm going to use the concept of iron rusting. That's a great example of a chemical change. That iron bar is no longer iron anymore, at least on the surface. That the iron atoms on the surface of that substance have reacted with oxygen to become something completely different. Or like, for example, something exploding, like dynamite, TNT exploding. When an explosive explodes, it's no longer the same substance that it was before. And these pictures on the right kind of illustrate various types of chemical changes. Letter A there is putting copper metal in nitric acid. You can see the copper metal. Copper is normally like kind of like a shiny brownish color. And now putting in nitric acid, you can kind of see that it's forming these blue copper compounds here at the bottom. Lighting a match. That combustion is changing what is making up the wood in that match into something else. Cooking food is a great example of a chemical change. When you cook food, say like meat, what you're doing is you're breaking down the proteins and the enzymes and everything that's in there, and you're not physically, you're chemically changing, permanently changing those substances that are in that food. Or like when food rots, again, that's a process of changing the food permanently. It's not a change in state. And that will pretty much wrap up this part of the chapter. And again, I want to emphasize that we're not covering all of chapter 1 right now. This is kind of just like the introduction to chemistry. We will come back and we will finish chapter 1 in a few weeks, but this is where this first part of our GChem experience will end. So if you have any questions, please come see me in office hours or talk to a tutor or both. But feel free to email me or ask questions at any time, and I'll be more than happy to help.